Dear friend, in this module, we are going to see the pharmacokinetic basis for the bioequivalence. In the previous modules, we have seen what is bioavailability, what is bioequivalence, all those things. So here, again, we'll recap that. So the bioavailability is the rate and extent at which the active ingredient reaches the systemic circulation and the site of action. Here, this particular diagram shows about the oral bioavailability where the drug is entered into the gastrointestinal tract, and from the GI wall it get absorbed, goes into the portal vein, and it goes to the liver, and also it goes to the systemic circulation through the bloodstream. So the drug which goes to the liver sometimes get or undergo first pass metabolism. Remaining drug reaches the systemic circulation. So this is how the drug absorption happen after the oral administration of drug products. This particular diagram, the other diagram on the right side, is denoting the intravenous administration as well as the oral administration pharmacokinetics comparison. So the diagram shows the oral administration in the lower part where it is highlighted with the red color. The oral dosage forms looks like a bell-shaped curve where it starts from the lower part of the graph and goes up and comes down. So this is like a bell-shaped curve where from the baseline the drug concentration from the zero it increases to a level, and again after distribution and excretion it comes down to the baseline. But in case of intravenous, you can see it start from the top of the y-axis. Once you administer the drug through intravenous route, the drug concentration is 100%. It is the highest concentration available at the start, and then after distribution and excretion, it started to decline, come to the baseline. This particular slide further explains the difference of pharmacokinetics between the oral dosage form and the intravenous bolus administration. So the graph here in the left side, which denotes the oral administration of the drug, where we can see the bell-shaped curve, and here y-axis denotes the drug concentration, x-axis denotes the time. So time versus plasma concentration or the blood concentration is the overall graph representing, and the individual pharmacokinetic parameters are explained here in schematically, where the Cmax is the maximum concentration observed in the particular diagram, and the Tmax is the time to reach maximum concentration, and then the AUC is the area under the curve, which is highlighted with a light green color. And the right side you can see bolus administration pharmacokinetics, where it starts from the top of the y-axis and comes down. And here also the comparison is given vis-a-vis the oral dosage form. So the drug which is injected comes to the baseline from the top to the down, and the determination of bioavailability here is the relative bioavailability and the absolute bioavailability are defined. The relative bioavailability is comparison of two dosage forms where you are comparing a oral dosage form with another oral dosage form where your relative bioavailability is assessed. So the relative bioavailability is AUC of one oral dosage form to the AUC of another dosage form. So that is called relative bioavailability, and the absolute bioavailability is against the oral vis-a-vis the intravenous bolus. So here this bioavailability is formula is denoting the absolute bioavailability where your oral bioavailability is compared with the intravenous bioavailability, which is 100% always, against which you are calculating the oral bioavailability. So this is the difference between the absolute bioavailability and the relative bioavailability. So this slide representing the important pharmacokinetic parameters with respect to the absorption, and here you see the bell-shaped curve where the drug concentration starts from the baseline and going to the maximum concentration and comes down to the baseline, and you can see the Cmax at which the maximum concentration of the drug is absorbed, and this is the time to reach maximum concentration, and you can see the therapeutic range could be the minimum effective concentration somewhere below the Cmax, and the maximum toxic concentration it could be much above the Cmax. So this is called the therapeutic range. Above probably this particular line we have the safety issues, and below this particular range the drug levels may not be effective. This is what the therapeutic range explains. And this particular area is duration of the action. Probably from this time to this time, the duration of action will be happening. And eventually the AUC is highlighted here with the gray color, which is measured by the trapezoidal rule, which we are going to see in the upcoming slide. So in this slide, we are going to see the AUC calculation, how the AUC is being calculated. This is the typical intravenous bolus administration curve where the AUC is calculated by the trapezoidal rule. So what is the trapezoid? So here is the shape of the trapezoid is given. So this is called the trapezoid where you have different dimensions of the four sides of the particular trapezoid, and this trapezoid area is calculated by this formula. If you divide this curve into equal lines across the curve, you will have multiple numbers of trapezoids. So each the area will be calculated using this particular formula. So when you add all this trapezoidal area, you will have the AUC value. And in case of oral administration, you will be having two triangles also along with these trapezoids. So the number of trapezoids areas and the two triangle areas will give you the AUC value for the oral administration of the bell curve. So in case of oral administration, you will have this kind of bell curve. So I am trying to explain you how the two triangles has to form for the calculation of AUC. So when you have these trapezoids for the calculation of AUC, so different trapezoids are formed here. So by adding different lines, and one, two, three trapezoids we have, and you can see the at the start and the end two triangles. So that's how trapezoids are here. At least three to four trapezoids are here to calculate the area, and two triangles. This is how the area of under the curve of the oral administration will be calculated. So now we come to the elimination parameters. So different elimination parameters are being calculated using the plasma concentration time curve. So the plasma concentration time curve is converted into logarithmic scale. So the y-axis represents the plasma concentration and it will be converted to the log scale. And once it is converted to the log scale, we can calculate the elimination parameters using the different slope of the curve. So the slope of the curve will be calculated using this particular line, and the slope of the curve used to calculate the elimination rate constant and the half-life. Once the plasma concentration versus time curve is converted to semi-logarithmic, that is, the y-axis values will be converted to log scale. You will have the curve like this, where the slope of the curve will be calculated by linear regressions. Once you make the linear regression, you will have the straight line like this. This is the straight line you can see. And once the straight line is observed, you can calculate directly the slope value, that is the m value, and the intercept value, that is the c value, by using formula y is equal to mx plus c. And otherwise, if you are plotting this in a graphical paper from the linear regression curve, you can calculate this m value by using this formula y1 minus y2 divided by x1 minus x2, or vice versa. So this is how the slope value calculated manually from a graph paper if you plot this entire semi-logarithmic curve. And once you have the m value and the c value, that is slope and intercept, you can calculate the elimination rate constant by using this formula, that is slope into 2.303, that is the log conversion value. And also you can calculate the T off by using the elimination rate constant, that is nothing but 0.693 divided by KEL. So far we have seen the basis of pharmacokinetics for the bioequivalence and viability. Now it is important to understand the factors which affect the viability, because this is critical when it comes to understand the type of bioavailability studies or bioequivalence studies we carried out for the pharmaceutical development purpose. So there are several studies we have seen in bioequivalence, like fasting steady fate study and steady state studies, etc. So to understand those types, it is important to understand the factors affecting bioavailability. So generally the physiochemical factors which affects the bioavailability are the API solubility or dissolution rate or salt form of the API also can affect the bioavailability. Then the particle and surface area which can affect the bioavailability, because the lower the particle size, more the surface area, which generally gives more bioavailability. Then the drug ionization, pH partition, pKa can affect the bioavailability, including the lipophilicity. More lipophilic the drugs, the more absorption in the gastrointestinal tract. Then the polymorphism of the drug particle can affect the bioavailability. Generally, the amorphous form have more bioavailability than the crystalline form. Then the drug stability. So, for example, you can see the prazoles, omeprazole, pantoprazole. So many drugs are entry coated in nature. So, why these formulations are entry coated? Because these are not stable in the gastric pH. So, these are entry coated by polymers and bypass the delivery of the drugs in the gastric pH region and deliver the drug into the intestinal region where the drug is stable. Now we come to the factors which are related to pharmaceutical or formulation, like type of dosage form. There are different types of dosage forms like tablets, capsule, suspension, solution. So the superior bioavailability or bioavailability will be there for the solution formulation because it is instant solution where the drug disintegration and dissolution steps are avoided. So solution have the superior bioavailability followed by the suspensions or maybe the tablet capsules, depends on the formulation. So here the type of dosage form can affect the bioavailability. Then the disintegration dissolution rate of the dosage form. For example, these tablets and capsule tend to disintegrate and dissolution. So the time required for these two phenomena can affect the bioavailability. Then the excipients and the manufacturing variables can affect, and then the product age and storage conditions can affect the bioavailability. Apart from the physicochemical parameters and the formulation related parameters, there are several physiological related factors which can affect the bioavailability of the drug. That includes the membrane physiology of the human beings, the structure of the membranes which is present in the gastrointestinal tract, then the transport process involved the absorption of the drug from the gastrointestinal tract. Then the gastrointestinal physiology, which includes the pH of the gastric as well as intestinal mucosa, then the gastric motility of the subject as well as the emptying and intestinal transit time. Then the influence of food can also affect the bioavailability. Then the disease state like liver damage or the kidney damage, blood flow to the GIT, age, pediatric population, adult population, geriatric population like aged people can have a different pharmacokinetics for different drugs. Then finally, the first pass effect can also affect the bioavailability. If there is a huge first pass effect, the bioavailability is reduced. In this, particularly more relevant to the bioavailability and bioequivalence studies are the pH and the influence of food. So the fasting state, the pH of the gastric area is more acidic than the fed state. And also the food, since the food is affecting the pH of the gastric area, the absorption of the drug can be different from the fasting condition to the fed condition. So the food also sometimes can increase the bioavailability by providing more lipophilic nature of the food milieu or lipophilic nature of the environment in the gastric area. So these two factors, food as well as the pH, are interrelated with respect to the physiological condition, which can affect the bioavailability. So in most of the cases, the bioequivalent studies are conducted in both fasting and fed conditions. And also there are food effect studies are being conducted where the dosage form given in the fasting conditions, the pharmacokinetics are measured, then the same dosage form given in the under the fed condition and the pharmacokinetics are measured, then the difference between the pharmacokinetics are reported. So with this, we come to the end of understanding of pharmacokinetic basis of bioavailability and bioequivalence studies. And moving forward, in the next module, we are going to see the different bioequivalence study designs and the protocol design. Thank you.